So let's get started. Welcome back, everyone. Hope you had a good long weekend. My stuff. Um, so, so let's see where we are on the schedule before we get into nearest neighbor searching. Um, Okay, so the first homework was due on Wednesday. Looks okay. We're working on grading these. My goal is to have them all graded by the end of the week. We'll see. This is a goal. We'll see how it goes, but that's hopefully the cadence we'll be able to go at. That when you turn them in on Wednesday, they'll be back by the end of the next week. We had Labor Day this week, and then there was the first one. So there's some stuff we're learning how to do with the TA and grading. So it might be a little bit longer this week, but that's kind of the goal on that. Your proposal is due next week, Wednesday. Let's look at what is the proposal. It's worth 5 points towards your project out of 100. The project overall is worth, what is it? 45% of the grade. So, okay, so make sure you turn in the proposal. I'm not asking for a lot. Okay, I want 1 to 200 words. Okay, so not too much. I'm going to go and read through all of them. Want to know kind of who is in your group. For me, this is the most important thing, that you have formed a group and you've started to work and to think about what is the topic you'll be, or like who you're working with. So you start talking with them, start making plans. Then what data you plan to use and where you plan to get it from. This is not a final decision on the data. This is kind of, what is your plan, right? What sort of data are you thinking of looking at? And what structure do you want to mine from the data? All right, so, okay, so this, again, it's a early proposal. This is not going to be a concrete binding contract. But I want you to start thinking about this and to put together a plan, and then you can refine it and change it over the semester. But most of you will find a plan and probably stick with the plan. Okay, so that's why I want you to start doing this now. Then, as you're seeing more techniques and ideas from the course over the semester, you will get more thoughts on what you can possibly do. You'll say, oh, that would be a cool thing to add into this. But that will click less if you haven't thought of a kind of abstract goal and the data you're looking at yet, right? And then why do you think the problem is interesting, and what is new, or what will the instructor, learn? One of my favorite parts of teaching this class is getting to review and give feedback and learn from what all of you do on the project. I learn all sorts of stuff, including what you try and does not work. I find this very informative. Or what you want to do and sometimes you don't know how to do, and I try and help you find something in the literature about techniques to do that. This has influenced the sort of things that we cover in the class, because I realize, okay, this topic, everyone was asking me, how do you do this? I'm like, okay, I better put a lecture into the class on this topic. Other times it's been, there's not a good solution, and then we end up kind of working research on that topic and coming up with new approaches for it, right? So, and some of the students, the class projects have turned into those research projects as well. I also wanted enough to be able to give some feedback on, is this kind of a broadly feasible project? I've been teaching a version of this class, not continuously, but quite a number of times. And I have a pretty good sense of what will and won't work. Not all the time. Sometimes I'm eager to find out, but I can give you a sense of, well, as you're planning it, it's not going to work, but maybe try this other version of it. And so I'll be able to start giving feedback on if this is feasible idea or not, or if you're not on the right track, right? This should be a data mining project and not a machine learning project. So you will not be building, you not be doing supervised learning in this project. At least you can use black box supervised learning for evaluation. You can say, I'm going to build some interesting features based on something else, and then apply some classifier at the end, not change that, use that fixed, and evaluate a couple different ways of building features. But that's not the point of the project. That's kind of some black box you're using to evaluate. Yeah. Oh yeah, I should. I have a whole bunch of posters I will bring in. Pretty far from my office this year. So I will bring in next Monday, I'll bring in a bunch of posters. I can't, for like FERPA reasons and stuff, I can't like post them online. But I'll bring posters into class, and you'll get, at the end, you'll make posters, and it'll give you a lot of sense of what these are like. Yeah. Thanks for reminding me. I should have brought them in this time. But I'll bring in a bunch of posters, and we'll lay them out, and you'll get to look at them. This is kind of a checkpoint, so you're getting on the way. It's not like the end point of the project, but I want you to get you thinking about this. All right, and it should be groups of 2 or 3, unless fairly unusual circumstances. All right, any questions on the project proposal? Yep, you can use all sorts of stuff, right? I hope you bring in outside knowledge and ideas from this class, but that you also demonstrate the ability of techniques within the scope of the class, right? So the things you bring in outside could be, often it's a data set or a challenge from outside, or it's domain knowledge outside, but it could also be you're integrating with some advanced other techniques from other courses, or you're involved in research and it's part of a research project, and here's the data mine part that plugs into that, right? Those are often, with the more you're able to bring in and really ground the project, the less abstract it is, like you're just looking at some Kaggle data set, the better the project will be. The more you're able to kind of bring in some authority beyond just the topics in the course. Okay, I don't want you looking at like these really clean generic data sets. Part of the point of this is to be looking at some data set where you don't know what the structure is or how to organize it or what to do with it at the beginning, and kind of working through that a bit. I don't want to make that it shouldn't be too onerous at the same time, but if it's like a super clean data set and you're just running a clustering algorithm on it, it's not going to be very exciting. Yeah. So, okay. If you have questions on this, feel free to come chat with me after class, office hours. You can send me email about ideas. Happy to give feedback, or I will try and give some when you turn in the project proposals. And what else? The next homework assignment, the similarity homework assignment, is due in 2 weeks. Okay, I posted it. It should be in Gradescope. I'm not sure it's 100% set up in Gradescope yet, but it's mostly there. I posted this is linked off the webpage, the document. You'll be working on doing stuff with similarity search, mostly looking at one of these GloVe data sets with the word vector embeddings. I picked a 100-dimensional one for you to use. In practice, people found for this sort of data around 300 dimensions is where you want to be, but it's a little bit going back and forth to TA. I think for some of you, that data set will be fine. You'll be comfortable using it, but it's kind of big and onerous to work with. The 100-dimensional one isn't that small either, but I think it's to be a little bit more feasible on kind of the average machine you guys probably have. Okay, so this is a large data set. And it's going to assign every word as a 100-dimensional vector, right? So you'll download it. the first question is basically just downloading it and looking at it and kind of looking at the first 10 or so words in here. Okay, probably for the sub problem, I think will give the most people or some fraction of people the hardest time will be 2A, where I'm going to ask you to load the data set into a vector database, sort of thing we'll talk about today. So you may need to get stuff installed on your computer to load it. And so that may be a little bit challenging. So if you're not too familiar with that, maybe try getting started on this a bit early, so you can ask the TA for help. She will, I think, plan to post a little bit more guidance, but these kind of links should hopefully help. You can use kind of some AI to help you navigate how to get installed. That's totally fine, and get it set up. All use of that is totally fine. But I want you to run this yourself. Okay. And then once you have it installed, you're going to run some operations on it. Okay. In the process, you'll be looking at some different distances. First one is cosine and angular distance. Second one will be Euclidean distance. And the third one will be, again, the angular distance, but with some locality-sensitive hashing. We won't really cover what's going on here too much until a week from now. So if you don't understand all of this, it may not make sense that we cover it a week from now, but you can get started on the other parts of the homework. This will be more of a randomized one, like some of the stuff you did on the first homework assignment. Okay, and then there's a bonus question. Again, the bonus question I'll mention there, as in terms of how hard is the bonus question, I think it's not the best use of your time if you're trying to only get up to 80 out of 100 points. But if you want to challenge yourself and do a little bit more digging, then these are great ways to do that. I'll be a little bit pickier on the grading it. This is kind of what's separating the cream of the crop in the class, as it often turns out. There are a few people who go after the bonus questions every year, but they're not required. You get to 100 points without doing the bonus. Yes. Okay. So please take a look at that, and you have a couple weeks to get started on that and kind of get questions with the TA or myself if you get stuck along the way. Okay. Okay, we're going to be talking about nearest neighbor search, and we're going to get into this kind of newer idea, the hierarchical navigable small world graphs. Okay, which is kind of a fairly new technology for how to do this. Okay, so nearest neighbor search, kind of pictorially, neighbor search. Okay, we're going to be given a data set X, and it could be an abstract data set where we'll say it's an RD. So these are d-dimensional vectors, and we'll be given a distance, a distance function, which will be defined right? So a distance function that tells us how similar two things are. For this talk, we'll mostly be saying that this is that D of A, B, or this lecture is just the Euclidean distance in between the two vectors. Okay, so I can draw pictures. A lot of this ideas will work with things like the angular distance and cosine distance, and most of the algorithms and software, at least the more modern ones, will work just as well if I replace this with the angular and cosine distance instead. And some of the other metric distances you can use for a lot of these ideas with some tweaks and variations. Okay, so again, the problem is we're going to be given some data set again, this is X. This would be some data point XI. And then you're going to be given a query. A query is going to be another element in RD. Okay. And given the query, I want to find the nearest neighbor. Okay, so the goal of the query is to find, I'll call this phi of x of q is going to be the arg min of x and x of the distance between x and q. Okay, so that I'm going to turn this point here, right? So you can think of it as there's a Euclidean ball around the query, and I want to find the smallest ball that contains exactly one point in the data set, and then this is the point that I'm returning here, right? So this would be x star. Okay, so I want to find the nearest neighbor in this data set. Okay, and so if I'm just thinking kind of, okay, not from a computational point of view, all right, this argmin tells me what I need to do. I need to check every one of the data points and then calculate the distance and return the min. Okay, and so I can compute all these things. But we're going to be dealing with quite large data sets. Your homework will have an example of one of these large data sets. And computing the distance to every single point every time you make a query is going to be too slow. Okay, and so I don't want to just directly calculate every distance. What I want to do is to pre-process x into a data structure S of x. So S of x is a data structure. And so then I can answer these queries very efficiently on the data structure. Okay, and so I would like to be able to answer this nearest neighbor queries as fast as possible. There are a couple of variants of this nearest neighbor query before I get past this picture. I may want to, so I could ask, so one is kind of nearest neighbor query of qx. And so this maybe it's a data structure S of x, and I would ask maybe I'll call this S sub x here. Okay, and now I'm going to ask, I've at S sub x, I'm going to ask a query, right? And this is going to give me x star for this query point. But I could also say a k nearest neighbor kind of query on a data set x. Okay, and so this would give me a set x1 up to xk, S of x q k. And so this instead is finding a circle that contains k points. So k might be, in this case, 5. So k equals 5, and I want the 5 closest points. So I can think of as growing a ball around the query point until it contains 5 points and return all 5 of those. So I want the 5 nearest points. This usually is about as hard, if k is small, about as hard as returning the 1 closest point. But it will be useful to think about this version of the problem as well. And this is often just as, so a lot of the software out there, including some that we'll talk about today and that you can use for your homework, will also allow these k nearest neighbor queries. And so it will use the same kind of infrastructure and everything for that. Yeah. Okay. So let's talk about how do we do the nearest neighbor search? And so I've drawn a picture in 2D, and ultimately, I'm going to kind of build up to the high dimensional problem. Again, we're going to be representing our data as very high dimensional vectors, and kind of what is something that's changed significantly since when I was in school is it was thought that it was never going to be feasible to do high dimensional nearest neighbor search, that was just an intractable problem. And that's kind of changed. And the story has kind of progressed over the last 20 or so years. And I'll tell you a bit about this story. And I'll do it by kind of starting from one dimension, and we'll kind of build up. Okay. And the story will have a few plot twists and stuff, so hopefully it'll keep you engaged. Okay. So one dimensional nearest neighbor search, and I think I've got a slightly different plan on how to present this that I haven't. It's not how I structured my notes, so we'll see how this goes. But I think I have a different way of how to give this lecture that hopefully gives insight not just to where we were and where we got stuck, but also where we are now. Okay, so the input now, so the X is going to be a subset of R1. So that means that I can draw a picture where there's a line, and then I've got some data points on this line. Okay, so this is my data set, and I can draw it spatially in just one dimension. And then I can have a query, going to have a query Q, which is also going to be a point in R1. And so the point is going to be a query Q, and then I want to find the nearest neighbor, right? So the nearest neighbor is going to be this point, right? This is the closest point onto the query. Okay, what's interesting about this, and the kind of the question where there's been a lot of development and proposals over the years, is how do I build a data structure to pre-process so I can do this efficiently, right? So if I have this data set, what is, and let me, before I explain this data set, I'm gonna grab this and put it on the next slide, because we're gonna try we're gonna give a second approach to this. All right, how do I build a data structure so I can do a fast nearest neighbor query in one dimension? Yep. Yeah, let's do binary search. Okay, so what's the data structure? Yeah, okay. So I'm gonna build I can store this in an array. Good. The array allows me to kind of, there's some tricks you can do once it's an array without actually building a structure. But if I were to build kind of a search structure on top of this, that I hear, I'll use a binary search tree, right? This is kind of a natural thing of thinking of the structure. And I want to kind of build a tree, and I will kind of build a tree like this, where I'm going to pair things up, and then there's going to be next level in the tree. Okay, so this is my binary search tree. And when I have a query, and so how do I think about this query is I'm going to have a decision point here, and this may store, this will probably store the information of this. Yeah, so of, let's say a little bit simpler, let's say of this data point. Okay, and then it'll store the rightmost data point in the left tree. Okay, and what it basically tells me is on a query, when I look at this query, I want to compare it to this value here and decide whether I should look down the left or the right tree. Okay, and so I want to compare the query to this value, and it says it's larger than this value, so I'm going to go down this right tree here, right? So then I'm going to take the query and make to this comparison. This guy is going to store this data point. And so now I can compare the query to this value. And I say, well, it's smaller than this value, so I think the nearest neighbor is stored in this left tree. And what this is actually doing is it's defining this region that there's this, I could think of this region here that after going to the, right, first going left and then going right, that I think, well, the query point is going to be inside of here. So the answer, the nearest point, is probably going to also be inside this region. Okay. And then this one is storing this point, and I'm going to again go to the left. This node is storing, and I have a data structure that's storing something at each of these nodes. Hopefully you've all maybe taken some data structure course. And so that tells me I can go left, and I get to this data point. I've narrowed it. So ultimately I get to this region here, and I know that the query is going to be in this region. And so what does that tell me? I'm at, I didn't draw that perfectly, this region right here. So I know the query point is in this region of the space. I can think of decomposing the space and quantifying the region. And I know that there are no, maybe in this case, there are no data points in this region. So the nearest neighbor, does it have to be this point? This is the point at the base of the tree. This is a candidate for the data point, or it might be the point defining the other side. To find this point on the other side, I kind of need to do this exercise and say, well, if it's on the other side of the tree, I need to go back up until the split and then come down here. Or I can also store these in a list, and I can hop to the one side of the list. But this yellow route will look more familiar when we go to the higher dimensional sort of setting. Okay, so it's defining a region, it's finding the best candidate in the region, and then it's checking nearby regions to see if they have a better candidate. The nearest neighbor must be one of these points. Okay, so this is one way of building a fast nearest neighbor search query for a data point in the real values. How long does this take? There are two questions of how long does this take. One is the build time. How long does it take to build this data structure? What? So it's n log n. Yeah, so I have to sort the data. So I sort in one dimensions, okay? If the data comes sorted, it only takes linear time to build. The space is linear, the size of the tree, there's only half as many things each time you're going up. And then the query time is going to be, what's the query time of this? So is log n, right? The height of the tree is logarithmic in the size of the point, right? I cut down the number of viable points in the region that I'm searching by half every time. So after log n steps, I reach them. Okay, so hopefully this is clear, and you've kind of seen most of these ideas before, if not this explicit thing before. Okay, well, let me tell you about another approach towards doing this in one dimension, called a skip list. Okay, that is going to be useful to know about a bit later. It's going to be building a similar structure, but how it does it is different. It's going to be a randomized algorithm. It's going to have roughly the same guarantees, but they're going to be randomized. So you'd probably think, okay, this seems better. I don't have to deal with randomization here, but this will be a useful structure. It has some uses in keeping it updated in just the one-dimensional setting. Okay, at every, what I'm going to do is I'm going to kind of keep track of a linked list on the data set here, but I'm going to do it in levels. And each level, I'm going to flip a coin, decide, am I going to elevate this point up to the next level or not? So this point, the first one is getting elevated to the next level. The second one, maybe I flip a coin, it's not. The third one is elevated. The fourth one is elevated. The sixth one is. The seventh one. The eighth one, you know, about, and I flip a fair coin. So about half of them should be lifted onto the next level. Then I build a linked list in between these. Okay, and then I do this process again. I again decide to flip about half of them to the next level. Okay, and then I build a linked list in between these guys. And then I again flip about half of them to the next level. And at this point, I can stop. Actually, let me use. Okay, so this is my skip list. It's random structure. I keep about half of them going up, so the height and expectation is still log n. On a query, I basically find, again, a query Q. I'm basically going to find, say, the region that is going to be the pair of points that the query point must be in between. And maybe I take the rightmost endpoint of this region. I go down here, and I am going to observe, well, it's the same region, so I didn't get much going down in this level in this example here. So then I'm going to go down to the next level, and then I can zoom in and find, well, it's going to be, I can jump down to the next level, and then I refine this region in the next level. Okay, and then finally I go down again, and I refine the region. And so again, I started with some region, and I'm refining this region each level, and then it must be one of the two endpoints in this region again. Okay, this is a skip list, the same kind of in expectation, the same asymptotic size and expected query time. I still need to sort, so they're still expected same time to build. Okay, yeah. So if I insert a point in the sorted order, I just flip a coin, or I to decide where I keep it, what level, and I just insert it there. If I delete a point, I never have to like do rotations or anything like that. So it's actually pretty easy to implement, and the data structure is actually simpler to implement. We'll come back to the skip list, and it will be an analogy for what we'll see at the end of the lecture for higher dimensions. Okay. There are some other very subtle reasons why you might want to use it, but it's pretty easy to implement this, and it works pretty well. Okay, another way to search in one dimension. The skip list, I would say, whereas this kind of really focused on the regions, I'm giving example of. This one is really identifying the kind of key points along the way. I mean, maybe this analogy will make sense a little bit later. Okay, let's talk about 2 dimensions now. 2-dimension nearest neighbor search. Okay, so now I've got my data points. Okay, and they may be like this. And now I have a query. And I need to find, again, the nearest point in Euclidean space is going to be, this is going to be the answer that I want to find. Now I can't use one-dimensional sorting anymore, right? And so, okay, so the computational geometry perspective on this problem is actually you need to build what's called the Voronoi diagram, which is taking all the bisectors. Let me try and draw this between all of the points. And what it's doing is it's doing here. So something like this. Okay, so I've divided up the region into this space into these regions, and in order to determine what the answer for the query is, it determines exactly which region the query is. That corresponds to this point. If I cross over this bisector, it becomes closer to this point instead. Okay, and this is an exact kind of decomposition of the space and is a mapping between where the query is and what the answer is. And this is precisely describing it. So if I'm answering a query, I basically need to determine which of the cells it's going to be in. And this is how computational geometry people thought about the question, and this led into how data structure people thought about the question. And so in order to kind of, in one dimension, it was still intervals, right? And it was easy to kind of think about. It was easy to represent this. It turns out in 2 dimensions, you can represent the Voronoi diagram in linear space. It's always of linear size asymptotically, the linear the number of points. And you can query which region it's in log n time exactly by doing some sort of space decomposition of this. And so the answer was I could get same linear space n log n kind of construction time and log n query time, right? So this also you can be used to do n log n construction, O of n space, and O of log n query. Okay, and this is for d is equal to 2. The problem is this Voronoi diagram becomes more and more complicated in higher dimensions. And the problem is that the space is going to be it's going to be theta of n to the d over 2 ceiling. Okay. So in high dimensions, the space of this is going to be exponential in d. So if d is equal to 2, this is linear space, but when d is equal to 3, it's going to take quadratic space. You store n squared stuff, right? And d is equal to 100 dimensions at n to the 50 dimensional space. I need to store like all of these edges, and you get these edges become higher dimensional, k-dimensional faces. It becomes very complicated. But this is the exact representation of the nearest neighbor. So if I want to answer a nearest neighbor query exactly, I essentially need to store this structure somehow or recompute it on the fly. and becomes very complicated to do. Becomes very hard to work with this exactly in higher dimensions. Okay. So this was this worked amazingly well in 2D, a great success, but it kind of leads to a dead end in higher dimensions. Okay. So instead, what people do is they will do approximate nearest nearest neighbor search. Okay, so let's say that x star equals, again, this is the arg is the arg min is the nearest point, and I want to say an epsilon approx nearest neighbor, we'll call this x hat epsilon, is such that the distance between the query and x star is going to be less than distance to the query and x hat epsilon. This has to be, because this is the smallest possible distance, but not too much less than. Okay, so 1 plus epsilon, let's think of setting epsilon equals to 0.1, so 10%, so that it's always greater than it's never smaller than the smallest distance, but it's not more than 10% larger. And I can set this parameter epsilon. Maybe I want this to be 0.5 or even 1, then it's no more than twice as far. And this is, okay, I'm not getting the exact nearest neighbor, but it works pretty good. And maybe I find the k nearest neighbors approximately, and then I check all the k nearest neighbors I found, and probably the nearest neighbor is in there. Okay, and so I'm willing to relax this nearest neighbor search to this approximate version of the nearest neighbor search problem. And then people looked at this, and there are both, and let me describe the heuristics that people first were using. And then I'll mention the locality sensitive hashing, which we'll get back to in a later lecture, which kind of solve this from a theoretical point of view. Okay, so in order to do this, I'm going to have a data set. And instead of the Voronoi diagram that I needed to build on the data set, I'm going to instead do an easier sort of decomposition. Is it too hard to read something? Is it up there? Okay, good. Okay, so instead of doing the Voronoi decomposition, which is complicated and high dimensions, doesn't work so well, I'm going to do a orthogonal decomposition. I'm going to think of dividing the data set into the left part and the right part. And then looking at the left part, I'm going to divide this into a top and a bottom. The same with the right part. These can be separate splits, right? And then I will split again each of these parts. Okay, and I keep wanting to do these orthogonal decompositions until I've got exactly, say, 1 point in each of the cells. Or maybe I stop when there's a constant number of points in each of the cells. From a data structure perspective, it's easier. You stop a little bit short, and then you do brute force inside of cells with like 10 points or so. Okay. But for this illustration, I'll keep splitting until exactly 1 point is in a cell. Now on a query, how do I deal with this? So let's say my query is here. Okay. So now I've stored this again in a binary tree. And each of the splits, I need to make a decision on which way to go. Right. So on the first level, this big left-right split, I'm going to go to the right. The query is on the right. Then I'm going to go above on this one, above on this up-down split, and then to the left on this split. And ultimately, I'm going to be in this region. And there's one point in this region. And I'm going to say, well, this is my guess of the nearest neighbor is this distance here. Okay. And I did not get the right answer. Okay, but I did pretty good. This kind of simulates what this binary tree search was doing, but now I'm splitting in these orthogonal regions. In fact, the Voronoi diagram approach also simulated what the binary tree search is doing, but you could guarantee to find the right answer in log n time in 2D. Okay, so now, if you remember the second thing we did, we said, well, I found in the region this corresponds to an element of a binary tree again. I found the element in here, but it may have been the other side of that region, the other thing dividing it. So I need to kind of backtrack up the tree again, right? Remember, like I did in this picture, I found this one. To double check that this was the closest thing, I need to backtrack up the tree until the split I found the other side. It turns out I need to go the root and then come back down. That'll be the case in the example in 2D again. I'll need to come back down and find the other thing that define this. In this case, with this is called a KD tree, a k-dimensional tree, and I keep choosing left or right or up or down how I split. Or in D dimensions, I keep iterating between the different dimensions which way to split. There might not just be one thing I need to check here. There's not one other thing on the other side of the boundary. What I can do is I can go back up the tree and I first consider, well, how about this decision I made here? I made this decision on this split, left or right. I went to the left here. My query is this distance. Could anything on the right of this blue line been closer? Do I have to check anything on the right? Why not? I found one that's closer to the boundary of the cell. This green circle does not cross over the blue boundary, so I do not need to look in this part of the tree. I pruned part of the tree. I have a similar thing going on this decision. I don't need to look in this part of the tree, but it does cross over this line here. This is now a problem. The green circle crosses over here. Okay, now I have to go and run the same decision on this tree, right? And I have to go back and query again, and I go this direction, and I go here, and then I guess I would go here, and I would find a slightly smaller ball here. Okay, and now I found a closer thing, but now I need to go backtrack up this tree. I need to also, I have to do more of this bookkeeping again. I need to check across this line. It turns out I still need to check, but there wasn't anything closer. Then I need to check on this line. This one was safe. And I need to check on this line again. This line, this circle maybe is crossed over this line here. And so I then would need to go down this part of the tree, or possibly not. Okay. If I'm doing there are versions of the KD tree that people discovered where you could guarantee that you never have to search the whole space. If you choose the decomposition correctly, you get something like, I search like n to the 3/4 of all the points at most. Not log n, but a polynomial, sublinear polynomial. Not the KD tree, but some versions of these split trees. But the more important insight is that even if I just use a KD tree and I allow approximation, this allows me to prune much quicker. If I'm allowing to do this, once I found a circle, I only check if a shrunken version of that circle crosses over. If a shrunken version of the circle does not cross over, shrunk by a 1 plus epsilon factor, does not cross over the cell, then I don't need to search there. And that allows me to prune much more of the tree. And that greatly improves the efficiency in practice. Not much you can prove about this, but in practice, you can scale this up quite efficiently. So in practice, to say D equals 12 dimensions, okay? Remember when I was probably about your age, 20 or so, remember I was doing this on some 12-dimensional data sets, and it worked really well. You can get this to scale up if the data set is not really adversarial, and the queries aren't, then you can get to maybe 12 dimensions, and it works pretty well with this pruning trick. Okay, and then people said, well, if I do data adaptive splitting instead of always left or right splitting, I kind of always try and cluster the data and do the best split. Maybe with data adaptive splitting, you could get this up to D equals to, say, 100, 120, 128. There was this famous SIFT approach in computer vision that represented parts of images as 120 dimensional vectors. And for a long time, this was widely used everywhere in computer vision. For a long time, they used a version of the KD tree to do the nearest neighbor search on it, which was really important for image retrieval. This changed us from being able to search for images based on color, which was the state of the art 20 years ago. You said, here's a picture, find nearby pictures. Now you have generative models. You'd have a picture that had the sky in it. You'd see other pictures that were blue. That was the state of the art like 20 years ago. And then SIFT came along, and you can find features like you can identify cars and people's faces based on these SIFT features. And you have to do this kind of high dimensional, 128 dimensional search. And versions of this was the state of the art in practice for a long time of how to do this. Okay, some version of this this KD tree approach. Okay, this kind of makes sense. Okay, how many people have heard of the KD tree before this? How many people is this new ideas? Okay, if you were to implement from scratch up to even 5 years ago, I probably would have told you to start with this. This is not too hard to implement if you've done other data structures before. And then you kind of, the difference is you would choose a split in high dimensions. You choose a split that kind of you do a 2 clustering of the data set and found the best split, like find the best way to split it in 2 ways and adaptively do this. You'll get up to about 100 dimensions on most realistic data sets. There are better techniques now I will start telling you about, but this worked reasonably well. And the orthogonal version, you can optimize more because the comparison is now just looking at 1 coordinate, and you can do that even faster. So if you really get into optimizing this sort of stuff, the orthogonal one, you can optimize more in lower dimensions. But it's less adaptive to the structure of the data. Okay, I'm not going to spend as long talking about this because it's kind of been known, it's not the state of the art anymore. And the challenge with high dimensions, okay, is that we're trying to solve something that looks like this, where I have a query and I have a ball, and I want to find the smallest empty ball, basically, right? The smallest empty ball is going to be one that has 1 data point on its boundary, but it really is this round ball. And I'm doing with a decomposition, a space decomposition that looks like this. And the space decomposition, no matter how you do it, has corners. And so is basically going to be kind of these rectangular square sort of shapes. So the best you can approximate. So I'm basically trying to fit a ball inside of a square. And this is kind of the approximation I'm fighting when I'm doing any of these sort of approaches. I'm fitting a ball to a square, and you look at this picture, you say, well, that looks pretty good, right? I can fit a square around the ball, and it does a pretty good job. Okay, so what I want to tell you is that in high dimensions, this starts to be a really poor approximation. Okay, and so the way I like to think about this is comparing a ball of radius 1, okay, that what is the volume of this ball? Okay, so it's as a function of d. Okay, and so who knows what the volume of a ball in high dimensions, what the formula for this is? Okay, you probably don't know. I would know if it wasn't in my notes. But it's if the radius is 1, the volume of it is going to be, and of course, it involves pi, right? It's going to be pi to the d over 2 divided by the gamma function, okay, of d over 2 plus 1. Okay, you probably don't know what the gamma function is. Okay, but this is pi of d over 2, and it's for even values of d, I think, or for even values of d over 2, this will be about d over 2 factorial. Okay, so the volume of a ball of radius 1, right? So we're thinking of, I've got the origin here. I'm going to say that the radius here is 1. Okay, the radius is 1. The volume is this quantity, pi to the d over 2, divided by d over 2 o factorial, right? And, okay, so what happens as d gets bigger? What happens as d gets bigger here? So it starts out being greater than 1, right? So if d is, let's say, 2, right, then this is pi divided by 1, right? So for d equals 2, this is going to be pi, right? For d equals, let's say d equals 4, I think this is only defined properly for even values of d, then this is going to be d squared divided by 4 factorial. What's 4 factorial? That's 4 times 3 times 2, which is 24. So now I'm going to have pi squared divided by 24. That's going to be, about 1/3, right? And so in general, as d gets bigger, the factorial term is going to grow more. This has the product of a bunch of pi's. This has the product of d over 2 pi's. This is the product of d over 2 values, but they get bigger and bigger. The first few are smaller than pi, and the last ones grow with d. So this becomes bigger. That means that this goes to 0 as d goes to infinity. The volume of d goes to 0. Okay, so it becomes smaller and smaller. Okay, let's compare this. Okay, so the details of this and this formula are not so important, but I want to compare this to the volume of a box of side length equals 2. Okay, so this is the bounding box up here. I want to compare this volume of the ball to the volume of this box as the dimension gets big. This is going to be the smallest box that contains this ball. Okay, so I want to fit the smallest box that contains the ball. This one should be much easier. This is going to be equals to, what's the volume of it going to be? 2 to the d. Okay. What happens with the volume of this as d gets bigger? It's growing, and it's growing exponentially. This one, it's not really growing very much. And in fact, it's shrinking down to 0, but it's not getting bigger. This one is growing exponentially. So the volumes diverge exponentially as the dimension gets bigger. You say, how can that possibly be? Well, the area in these corners takes up more and more of the area. And this becomes a worse and worse approximation. And so any of these space decompositions, they somehow have these corners, and these corners are somehow going to be a worse and worse approximation of the Euclidean ball. If I use maybe an L infinity ball, which is kind of a weird distance measure to use, maybe I don't have this issue, but it's still not. But for an L2 ball, which is often what we want to use, it's a really poor approximation high dimensions. Okay, so it's a little bit of high dimensional math. Okay, let me just say for just like 3 minutes, locality sensitive hashing. Okay, so from about 15 to 5 years ago, 20 to up till about 5 years ago, people thought locality sensitive hashing was the savior. Okay, this is a randomized data structure. Okay, and it uses hashing tricks, and I'm not going to describe it much now, but it's space and query time and construction time do not depend on D. Okay, they do depend on D in that you have to read the vectors, and a vector of length 300 is going to take 3 times as long to read as one of length 100. Okay, so it depends on the dimension in this way, but otherwise it does not depend on dimension. If you think the cost of reading an item is constant, then the space, query time, and construction time do not depend on dimension. Okay, it depends on the approximation factor. It says if I want for an epsilon approximation, the time space depends on epsilon, on only the epsilon approximation that you care about. It uses the randomization tricks. Okay, and for I'll just give you a preview for epsilon equals 1. So I'm getting a 2 approximation. So I'm getting a factor 2 approximation. Then the space is going to be O of n to the 8/7. And the query time is going to be O of n to the 1/7, approximately. There's some lower order terms here. Okay. So it's not going to give logarithmic query time, but it's going to give a small polynomial, n to the 1/7 if n is 10 million. How much is n to the 1/7 of 10 million? So it's 10, right? Or 1 is 10, right? Yeah, so if you have 110 million points, this is basically a constant in theory, right? There are some constants involved here in randomization. And so this kind of developed a lot for the last 15 to 5 years ago. And this is kind of theoretically so optimal in terms of the space and the runtime. Okay. And there were people who engineered these systems, and the big like tech companies, Microsoft, Google, they all have their own version of this software. Microsoft one called Falcon was especially good. Falcon is some software that is built on this nearest neighbors locality sensitive hashing. and it was well optimized, and kind of for a while was kind of the state of the art approach here. Okay, there's the work on that's kind of stopped for high dimensional nearest neighbor search. It's useful maybe in other abstract data types. It's maybe more general, but because there's another approach which works better than this. So hierarchical, navigable, small world. Okay, hopefully I don't have to say this again. This HNSW approach, this is a graph-based approach. And it's kind of an extension of the skip list. But think of a multi-dimensional skip list idea here. Okay, so let me try and illustrate this, how this works. Going to have two-dimensional sort of data set. And so I'm going to start by building a k-nearest neighbor graph. Okay, how do I build this graph? They kind of use the data structure as they're building it to build the graph, but don't worry about that. So well, I'll come back to these issues, but like, let's build a 3 nearest neighbor graph. Every node is connected to its 3 nearest neighbors. Let's say that guy's nearest neighbor is there. Okay, let's say this is the k-nearest neighbor graph. I'm going to get a query here, and I want to find the query using the k-nearest neighbor graph. Okay, so what I do now is I'm going to use the graph structure and nearest neighbor search on the graph. I have an entry point. Okay, I pick an arbitrary point to start. Okay, and what I'm going to do, I'm going to start here, and then I'm going to look at all of its neighbors and see which one is closest to the query. I look at the 3 edges coming out of this point and say which one is closest to the query. Turns out it's going to be this one. So I move to this one. It's closer than this is closer to the query. Then I say, okay, which of this guy's nearest neighbors are closer to the query? And well, so maybe it gets stuck here. This one is maybe further from the query than this guy. So then I stop. Okay, so this didn't work that well. The true nearest neighbor is over here. Okay, this was intentional that I would stop here. Okay, so but this would roughly be how it's worked. Otherwise, I would look, if this was the nearest neighbor, then I would look at its neighbors and its neighbors until I get here. Okay, it got stuck in a local minimum here. And this idea was not like new until there's a bunch of people from Russia who started implementing this and trying it, and it worked really well on high dimensional data with a few tricks. Okay, this idea that you could get stuck in a local minimum here and you wouldn't find the answer is why no one pursued this idea until some people said, we're going to try it anyways. Okay, and there are a couple of things they did instead of doing the first key idea, which I'll illustrate here, which doesn't involve skip lists, is so the first key idea is going to be doing beam search. Okay, so who's taken an AI class or heard beam search before? Maybe. Okay, so the beam search is when I'm searching for the best option in like a graph or something like that. But I'm not keeping just the best thing I've seen. I'm keeping the best T things I've seen so far. So I keep a buffer of the T best option I've seen so far. And let's say an example here so I'm going to keep T best options so far. Okay, and we'll do an example with t equals 2. Okay, so I will start here, and then this will be the nearest neighbor, and maybe this guy will be also closer. So my beam search after step 1, I'm going to keep these two things around, not just the closest one, but the best 2 options I've seen so far. And then I say, well, this one is stuck, but it has another neighbor. And so now I'm going to update my set. So it's this one and this one. These are now my 2 best options. This one, I've already exhausted all of its nearest neighbors, but this new guy, I haven't. So now I check all of his neighbors, and that includes this guy over here. And so now I update my beam to include this guy, which was already a good option, and this guy, and now say, well, this guy still has neighbors, and I check, and now he has this other neighbor over here, and now this guy's even closer, and now both of these, and in fact, this is the next best neighbor, but I can stop the beam search because neither of these have neighbors closer than either of those 2. Okay, but by keeping 2 or usually like 5 things around in the buffer, becomes much more robust to these these local minima. Okay, yeah. Yeah, how can I keep a guarantee about this? I can't. Okay, currently we do not know when and why this works so well. It's a really big active question. There are some, it depends on how you form the graph, turns out to be part of it. I need to, if I just use a knn graph, I can construct examples where this is not going to work. There are other strategies of how to construct the graph, and in some of those, we can have some sort of guarantees about that beam search will work. And I will give you the next slide, let me say, better ways to build the graph. So this was one important idea, this beam search, keeping a buffer of, say, 5 things around or doing k nearest neighbor search instead of 1 nearest neighbor search makes it much more robust in the searching process. I'm much less likely to get stuck. Okay. The other thing I need to make sure the graph is connected, and I want to make sure it's navigable. It's kind of, I can quickly get from anywhere to the proper answer. If I have a big planar graph that's really spread out, all the nearest neighbors are spread out, and I may need to walk very far along the graph to get from my entry point to the true answer. So I also want to handle this issue, right? Not only might it get stuck, it might just take a long time to get to the answer, and I may have to look at a linear fraction of the data to get there. So I don't want that to happen either. Okay, so the second big, question.
Is it possible to, let's say you're in a cluster, so there's multiple clusters. Let's say you're in a cluster and you're slowly getting there. Would it be smart to, at some point, I forget what it's specifically called, but I remember being taught this semester or 2 ago, you can randomly restart and choose a new starting point?
Yeah, so you could randomly start the entry point. That could be it. I'll give you a better strategy based on the skip list idea. Okay, so I'm going to build a hierarchical kind of graph. Okay, and so let me kind of draw a picture of the graph down here, and think at this level, I'm going to build the knn graph here. And this graph does not even need to be connected, right? I had to draw this extra edge before. This edge actually wouldn't be here in the knn graph, right? I drew this in to make this example work, okay? But it doesn't have to be connected, but I build like a knn graph at the bottom. But now what I'm going to do is I'm going to build a copy of the graph where I'm going to elevate half of the nodes. Maybe it could be different fraction here. So I'm thinking of building them up to the next level of the graph here. Okay, and then on this level, I'm also building a knn graph. This graph is going to be, the edges are going to be longer. Okay, and then I repeat this again. I'm going to lift these guys up again. Kind of like I did with the skip graph. Okay, and then I'm going to again build a knn graph here. And these edges are even longer. Okay. And I do this, I can think of doing this by, for every node, I flip a coin and I lift it to the next level, right? So I have these different levels here of the graph, and half, each time I go up a level, I have half the size of the graph. So I have log n of these levels. If I flip, I might even make it so I'm forced, I only have like maybe 5 levels in the graph. Maybe that's enough. I don't need to cut it by half every time. I could cut it by a much smaller fraction. Okay. Now, what I'm going to do is I'm going to enforce that my entry point is always going to be in the top graph. Okay. And let's say the query is here. Okay. And the query is going to be lifted up to each of these things. And so I'm first going to solve the nearest neighbor problem in the K-graph on the top level. Once I've solved it here, now this one is very small, so constant time, I can solve this one. Then I'm going to drop down to the next level. Then I drop down, and then I'm going to solve it on this level here. And so usually, because the graph is getting smaller and smaller and the edges are longer, I only make a small number of steps on each of the levels, right, before I solve it. When I get here, then I'm going to drop again. And now I'm usually going to be in the close area, and maybe this is the solution, or maybe it's over here. Okay. And so I'm always solving it on the top level. That means I'm going to move really quickly to get to about the right area, and I'm kind of zoning in, like I would with the kind of the skip graph or the binary search tree. And then once I find it, once I get close, then I do the very local search at the bottom. Okay, and if I do beam search, where I'm keeping track of a bunch of things, then I don't try and do the backtracking. I no longer have a spatial decomposition anymore, so I can't do like backtracking guarantees, because that spatial decomposition is not really working here. I'm building the graph instead. But the beam search kind of takes the place of that. And I'm just kind of hoping for the best. Okay, you have a question? Yeah, so I would keep all the things in the beam at every level. Yeah, so I would, in case there was a split in the graph and I wound up on the wrong side, I would go down on both sides, right? Yeah. Yeah, there are a bunch of variations of this now. This kind of came out of a group of Russia who no one was paying attention to. They wrote a number of papers, and then about 5 years ago, people started really paying attention to this, and there's been an explosion of techniques and a bunch of different approaches to this. There's some companies, former kind of a former a collaborator of mine started a company called Pinecone, which is valued at like $1 billion. He started it just a few years ago. That's basically is building versions of this. There is, so the kind of examples, Pinecone is a company, so they don't have public available software. Disk, ANN, is out of Microsoft. Disk ANN has some nice properties in that they have a slow construction and a fast construction. The slow construction, which is too slow to be practical, you can actually prove things about, that it will have some guarantees about conversions. Okay. And then there's a FAISS out of Facebook. I mentioned this one. This one pioneered another idea that I won't describe here, but it quantizes the results. So it basically stores the bits of the coordinates of the points in a distributed way. So at first it stores the top level bits at the top layer, and then it's adding more and more bits of precision to the data points as you go down. And this, if you do implement this really well, you can get a lot more savings out of this and speed up out of this. And so the FAISS, the Facebook version, is really efficient for that version. That's become kind of a standard trick as well. And then there's another one for the homework that might be easier to use called knn-graphs. Less well optimized. It's an older version, but it might be easier to get up and running. If you get face up and running, I would recommend doing that one. That one's kind of a open source kind of standard baseline. There's also some research level ones that probably beats a bunch of these in various kind of scenarios as well. Yeah, okay, we'll stop here. You will get to play with these things on your homework. They become a real staple of dealing with high dimensional data sets. So I want you to be kind of working and playing with them. So.